So in this video, I'd like to do one more example of a proof by induction, but it's going to have a little bit of a twist. So consider the proposition that 2 to the n is less than n factorial. So this is basically saying that the factorial of n is going to get bigger faster than 2 to the n. And we might try to prove this. So, but something funny happens. If we think about what our base case would be, so P0 says 2 to the 0 is less than 0 factorial. This is actually false, right? So 2 to the 0 is 1. 0 factorial is also 1. So 1 is not less than 1. Okay, so this is not true. Okay, what about P of 1? Is this ever true? And you might like to pause it at this point, actually, and try some values of n and see whether you think this is ever going to be true or not. So if we try 1, so this is not less than. It's not true for 1 either. This is 2, and 1 factorial is 1, so 2 is not less than 1. So P of 2 is not true. Right, again, 4 is not less than 2. P of 3 is also false, right, because 2 cubed is 8, but 3 factorial, 1 times 2 times 3 is only 6. But the next one, if we think about when n is 4, so 2 to the 4th is 16, and 4 factorial, 1 times 2 times 3 times 4, is 24. So this is actually true for 4. And if you tried it for 5, you would find that it's true there too, right? We're only multiplying this side by 2 to get 2 to the 5th, but we multiply this side by 5. And so we're going to get, over here we're going to get 32, and over here we're going to get 120. And so it does look like this will be true from here on. So our conjecture is that Pn, right, it's not true for all natural numbers, but we can say for all n greater than or equal to 4, Pn. And the way that we phrased induction before, we just said if you want to prove something for all natural numbers, and you start with the base case of P0. But it's very easy to adapt it when you want to prove it for some kind of subset of the natural numbers. All we have to do in this case is change our base case. So if our base case is P4, and then we also prove that for any k that's 4 or greater, it's P of k is going to imply P of k plus 1, right? Then P of 5 will be true, then P of 6, P of 7, and so on forever. So we're going to do a proof by induction, but we're just going to change our base case to be P of 4. Okay, so proof. Again, it's by induction on n. In the base case, P of 4 says right, that 2 to the 4th, which is 16, is less than 4 factorial, which is 24, and that's true. In our induction case, induction step, so we're going to say let k be an arbitrary natural number such that k is greater than or equal to 4. I only want to think about numbers that are greater than or equal to 4. It's not true for smaller ones. And then suppose that 2 to the k is less than k factorial, right? And this is our induction hypothesis. Okay, then Well, we want to show p of k plus 1, which says that 2 to the k plus 1 is less than k plus 1 factorial. So if I start with 2 to the k plus 1, right, that's equal to, well, I can pull out a 2. Again, I'm looking for a way to use my induction hypothesis that I've assumed. And it says something about 2 to the k. So if I pull a factor of 2 out of here, I'm going to get 2 times 2 to the k. So I can use my induction hypothesis. So this is 2 times 2 to the k, okay, which by the induction hypothesis is less than 2 times k factorial, right? So this is because of our induction hypothesis. And then 2, right, again, I'm trying to show this is going to be less than k plus 1 factorial. Well, I have a k factorial here, and if I multiply it by k plus 1, that'll give me k plus 1 factorial. And why do we know that 2 is less than k plus 1? Well, that's because we assume that k is greater than or equal to 4. So k plus 1 is at least 5, right? So 2 is definitely less than 5, or anything bigger. So since k is greater than or equal to 4, and this, of course, is equal to k plus 1 factorial. Okay, so thus p of k plus 1 holds. Right, and so again we say by induction we've proved that 2 to the n is less than n factorial for any n that is 4 or greater.